From the colossal bridges spanning continents to the humble spoon in our kitchen, one material has dominated the modern world: steel. It is the backbone of civilization, shaping our skylines, our vehicles, our very lives. But what if this bedrock of industry, so familiar and seemingly irreplaceable, were to meet its match? What if a challenger emerged, not from the established giants, but from an unexpected corner of the globe? A material that promises to redefine strength, weight, and even cost. A whisper. A claim. A potential revolution. In the quiet hum of laboratories, breakthroughs are born. But some breakthroughs resonate louder than others. Recently, a research team in China made an assertion that sent ripples through the scientific community. They claimed to have engineered a material poised to challenge steel itself. Not just a slight improvement, but a paradigm shift, a material that could match steel's formidable strength, while being dramatically lighter and, astonishingly, cheaper to produce. An audacious claim. A future without steel's heavy embrace. Is it truly possible? So, what exactly is this enigmatic substance? The details are still emerging, cloaked in scientific terminology. But the core ambition is clear: to fuse properties previously thought incompatible. To achieve strength without immense density. To innovate at a fundamental level. We're talking about advancements in ultralight carbon materials and nanostructured cellular solids. Words that conjure images of microscopic engineering, of atoms arranged with unprecedented precision. It's not just a new alloy, it's a new approach to material design. But how does this translate into real-world performance? The secret, it seems, lies in the architecture of the material itself. Imagine structures built not from solid blocks, but from intricate, microscopic frameworks. This is the realm of nanostructured cellular solids, materials designed at the atomic level to maximize strength-to-weight ratios. The team's research points to incorporating super lightweight magnesium alloys and even graphene into this equation. These aren't just additives, they are fundamental building blocks, each contributing unique properties to the final composite. But what kind of synergy can truly be achieved from such diverse components? Steel owes its dominance to its incredible tensile strength and resilience. It resists bending, breaking, and crushing with an enduring tenacity. To claim parity, let alone superiority, is to challenge centuries of material science. This new Chinese material reportedly achieves its strength through its unique internal structure, a network of interconnected cells and reinforced bonds that distribute stress far more efficiently than conventional solid materials. It's not about brute mass, but intelligent design. But can such an intricate design withstand the monumental forces faced in real-world applications? Beyond strength, the material's claim of being dramatically lighter is perhaps its most compelling feature. Imagine constructing with something that offers the robustness of steel but feels like a feather in comparison. This is the promise. By leveraging ultralight carbon materials and the inherent low density of magnesium alloys, combined with nanostructuring, the material achieves an unprecedented strength-to-weight ratio. Lighter components mean less energy required for movement, less mass for foundations, and entirely new possibilities for design. But how significant is this weight reduction, really? And what are its immediate implications? Strength and lightness are transformative, but often come at a premium. This is where the third claim truly astonishes: cheaper production. If true, this material wouldn't just be a high-performance niche product, it could democratize advanced engineering. Lower production costs could stem from novel manufacturing processes, or the abundance of its constituent elements, or perhaps a combination. Imagine the cascading economic effects if a superior material could be manufactured more affordably than its traditional counterpart. A truly disruptive force. But what does cheaper actually entail, and how would it impact global markets? If these claims hold, the impact on industries would be nothing short of revolutionary. Consider construction. Skyscrapers could reach new heights, with foundations requiring less material and lighter structural elements. Bridges could span wider distances, built with less environmental impact and greater speed. The very skyline of our cities might evolve, driven by materials that offer new architectural freedoms. Imagine structures that are not only stronger but also more adaptable, less costly to maintain, and quicker to erect. This isn't just an improvement, it's a reimagining. But how quickly could such a shift occur? Transportation would see a seismic shift. Cars, trucks, trains, and even ships could shed significant weight, leading to dramatic improvements in fuel efficiency and reduced emissions. Lighter vehicles accelerate faster, handle better, and require less energy to move. This translates to lower operating costs for individuals and industries, and a substantial step towards environmental sustainability. The pursuit of lighter, stronger vehicles has long been a holy grail for engineers. Could this material finally unlock that potential, transforming our journey from point A to point B? What could a truly lightweight car feel like? Perhaps no industry craves lightness and strength more than aerospace. Every gram saved in an aircraft or spacecraft translates directly into increased payload capacity, longer range, or greater fuel efficiency. This new material could make space travel more accessible, allowing for larger, more capable satellites or even new designs for reusable rockets. Commercial airliners could become significantly more efficient, reducing travel costs and environmental impact. The dream of lighter-than-air structures, once confined to science fiction, might edge closer to reality. What new horizons could we explore with such materials? Beyond these major sectors, the ripple effect would extend into general manufacturing. Everything from consumer electronics to industrial machinery could benefit. Products could become more durable, more portable, and incorporate radical new designs. Tools could be lighter, making labor less strenuous. New product categories might even emerge, enabled by the material's unique properties. This isn't just about replacing steel, it's about expanding the very canvas upon which engineers and designers create. The implications are vast, touching countless aspects of our daily lives. But is the world ready for such a seismic shift? But every grand claim faces formidable challenges. The path from laboratory breakthrough to industrial-scale application is fraught with hurdles. One of the most significant is scalability. Can this complex material be produced in the vast quantities needed to impact global industries? Manufacturing nanostructured cellular solids and incorporating specialized alloys like graphene on a massive scale is an engineering feat in itself. The processes must be consistent, cost-effective, and reproducible. A single prototype, no matter how impressive, does not guarantee a new era. The jump from beaker to factory floor is immense. Beyond initial production, there's the critical question of long-term durability. Steel has proven its mettle over centuries, enduring countless cycles of stress, corrosion, and wear. How will this new material perform under similar, prolonged conditions? Does it resist fatigue? Is it susceptible to environmental degradation? What about repairs and maintenance? A material designed for construction or aerospace must perform reliably for decades. These are not minor details, they are fundamental requirements for widespread adoption. Will its unique structure stand the test of time, or will hidden weaknesses emerge? And what of the claim of being cheaper to produce? While the raw material or manufacturing process might be less expensive, the true cost of adoption is far greater. It includes the vast investment in new tooling, new infrastructure, retraining of workforces, and the complex certification processes required for critical applications like aircraft and buildings. These hidden costs can make even a cheaper material prohibitively expensive to integrate initially. Will the economic benefits truly outweigh the enormous transition costs for established industries? The ledger is complex, far beyond a simple per kilogram comparison. Such extraordinary claims demand extraordinary evidence. The scientific community, by its very nature, approaches such announcements with a healthy dose of skepticism. Independent verification is paramount. Researchers globally will want to replicate the results, scrutinize the methodology, and stress test the material under various conditions. Until these claims are thoroughly vetted by peers outside the initial research team, questions will linger. This rigorous process is not a rejection of innovation, but a cornerstone of scientific progress, ensuring that breakthroughs are robust and reliable. What happens when the world's brightest minds turn their gaze? History is littered with materials breakthroughs that promised to change the world but never fully delivered. From advanced ceramics that proved too brittle, to superalloys too costly, the journey from lab marvel to industrial workhorse is treacherous. The hype around new materials, while often warranted by early results, sometimes outpaces their practical application. This context adds another layer of skepticism. Is this new Chinese material different? Does it genuinely possess the combination of properties and the underlying potential to overcome these historical pitfalls? Only time, and relentless testing, will truly tell. And we cannot ignore the broader geopolitical landscape. A materials breakthrough of this magnitude, emerging from China, carries additional weight. Intellectual property, technological leadership, and national security implications are all part of the equation. If successful, this could shift global economic power balances, giving a significant advantage to the nation that masters its production and application. This isn't just a material science story, it's a chapter in the ongoing narrative of global technological competition. What impact would such a breakthrough have on international relations and trade? Yet, for all the challenges and skepticism, the sheer what-if factor remains intoxicating. What if this material truly delivers? What if we are on the cusp of a materials revolution that fundamentally redefines construction, transportation, and every engineered product? Imagine a world where material constraints are vastly reduced, where sustainability is enhanced by lighter, more efficient structures, and where innovation is unleashed in ways we can barely conceive. The potential to solve complex global problems, from infrastructure decay to climate change, is immense. This is the promise that keeps scientists striving, dreaming of tomorrow. The journey from a promising lab result to a global industrial standard is long and arduous. It requires further research, massive investment, overcoming manufacturing complexities, rigorous testing, and gaining widespread acceptance. It will not happen overnight. There will be setbacks, refinements, and perhaps even redesigns. But the initial spark, the audacious claim from a Chinese research team, has ignited a fascinating conversation. It reminds us that even in the most fundamental fields, the future is always being written, one breakthrough at a time. And sometimes, the quietest whispers can change the loudest industries.